Welcome to lecture class meeting 9 of EECE574, graduate level probability and random processes. Today we have 3 announcements. Homework number 8 will be assigned and due next Tuesday. For this, you go to the PLMS. 2 supplementary handouts are uploaded to our primary course homepage. So as you always go, here I uploaded the Gaussian distribution related handouts. They are all handwritten around 10 years ago, but it will be very, very useful. So, and also lecture videos are available at the CISL.post YouTube channel. So if you miss something during the class meeting, then go to the channel and watch the video. So here goes the overview of this course. We are still covering the chapter 9 of the populist textbook. Especially, we are covering section 7, complex random processes. But since this course started directly from chapter 9, we didn't cover the complex random variables part and complex random vectors part. So I was covering in the last lecture the topic of complex valued random variables first. After covering that, we will be moving to section, the last half of the section 2 on the topic of time average and ergodicity. So yeah, probably I hope we can finish at least chapter 9 before our midterm exam. Here goes reviews. We studied the definition of complex random variable. What was that? What was the definition of complex random variable? It was a collection of 2 real random variables. And we call one of the pair as a real part and the other as the imaginary part. So that's all. That motivates how we define the CDF and PDF of a complex valued random variable. So it's very natural. Think about just a 2x1 real random vector. Last time I didn't cover how to define a characteristic function of a complex random variable. What do you guess? Just simple. You take the real part and imaginary part, and then define the characteristic function, joint characteristic function of these 2 parts. Got it? We also define the mean value of a complex random variable and variance of a complex random variable. The interesting part was pseudovariance. So what was the difference between variance and pseudovariance? What was the difference between variance and pseudovariance? So let's start denoting Z as a complex random variable we are concerned. And let's say mu as the mean. And here goes the variance, let me say. Yeah. Variance of Z defined as Z minus mu modulus squared, because this is a complex number, and in general, mu is also a complex number. Unlike the variance, complementary variance or pseudovariance just squares Z minus mean of Z. Okay, so they are different. In terms of the real part and imaginary part, what were they? The mean of a complex random variable was simply the mean of the real part plus J times the mean of the imaginary part. And how could we write the variance of Z and complementary variance of Z in terms of the variance of X, variance of Y, and covariance of X and Y? It's just simple. You plug in this. Got it? And anybody remembers? This was the variance of the real part plus variance of the imaginary part. Okay. And what was the complementary variance in terms of the three second order moments. Now you just expand and you will see the variance of x minus variance of y as its real part, and j times what? Covariance of x and y, right? So this shows that the variance itself misses covariance between x and y. And complementary variance has the covariance in the imaginary part. So in order to fully identify the second order moments of the real parts and imaginary parts of these two random variables, you need both of them. In order to have the variance of x, you take the real parts of this one and then add and divide by 2 to get variance. You take the real part of this, subtract and divide by 2, you get the variance of y. And okay, 2 is missing here. So by taking the imaginary part and divide by 2, you get the cross covariance between the real part and imaginary part. So pseudovariance is very important. However, in many cases, pseudovariance vanishes, which means that pseudovariance is 0. That is called propriety of a complex random variable. Complex random variable. Then what happens? What was the definition? This is 0 means that the real part and the imaginary part has the same variance and covariance is 0, right? So this definition is very useful because variance contains all the information. See that? Proper means this is 0 and they are the same, right? So given variance, by dividing it by 2, you can get the variance of real part and the variance of the imaginary part. And cross correlation coefficient is 0. So propriety assumption is okay in many cases. However, when your signal is a man-made signal, which means that it's not generated naturally, then it is likely that it is improper, which is not proper. So proper has the antonym improper. So you have a Venn diagram. Here is the set of all complex random variables. And the proper and improper means they are antonyms to each other. So you have here proper, and the complement is improper. By the way, there is another set often used in talking about a complex random variable, that is circularity. What was the definition of circularity? The definition is this: Z, a complex random variable, is circular if and only if, because you should be careful. When we define something, if means if and only if in lemmas, theorems, and propositions. So Z and e to the Z times e to the j theta have the same distribution, which means that in two-dimensional plane, so real part and imaginary part, you have the same PDF if PDF exists. What does that mean? The two-dimensional PDF must be rotationally symmetrical. For all theta, okay? So we can easily show that if a complex random variable is circular, then of course it has mean 0 if mean exists, and what is proper. So circularity is inside here. Got it? And here improper. Now, let's take an example, which is very important in especially communications engineering. That is a proper complex Gaussian random variable. So these all definitions and results are applicable. And in addition to them, we need Gaussianity. What does that mean? First, without this complex Gaussian random variable, what does that mean? The real part and the imaginary part are jointly Gaussian, real jointly Gaussian. That's simple, right? And in addition, we have propriety. By the way, proper has the noun form propriety. Got it? Right. So by adding propriety, we have a very interesting PDF. And what was that? That looked very similar to a real Gaussian random variables PDF, but there were differences. So let's take a look at this again, because this is so important. So suppose Z is a proper complex Gaussian random variable with mean mu and variance sigma square. First, whether it is Gaussian or not, proper means what? Proper with variance sigma square means what? The real part has variance sigma square over 2, and the imaginary part has the variance sigma square over 2. Now you have Gaussianity. What happens? So you may write the mean, the complex number, as the mu sub r plus j times mu sub I. Here mu sub r and mu sub I are mean values of the real and imaginary parts. Then what happens? Your real part and imaginary part has the joint density, what? Joint density what? You remember uncorrelatedness given jointly Gaussian random variables is equivalent to independence, right? So this joint density factors into marginal densities, and each marginal density is what? As you remember, let me move a little bit. I really love OneNote. Except this, I have to type the escape key times 1 over square root 2 pi sigma square over 2 e to the negative y minus mu imaginary square divided by 2 times the variance. So you have what? You have 1 over pi sigma square. Here sigma square is the variance of this complex Gaussian, proper complex Gaussian random variable. And you have here, due to the law of exponentials, powers, you have the summation of this. The denominators are the same as sigma square. And this is the real part and this is the imaginary part squared. So you have now what? Z minus mu modulus squared. Got it? So here you don't have 2. You don't have 2. You don't have square root. Got it? And you have a modulus squared, not just the parentheses, not just squared, modulus squared. Got it? So be careful. Okay, so we've done almost the proper complex Gaussian random variable part. And now let's see what we are going to study today. We are going to study a complex valued random vector or complex random vector. Got it? And we also study a complex random process, or some people love complex valued random process. And here goes something strange, complex valued vector random process, or some people say complex vector valued random process. And I will denote this by Z underscore or underlined Z. And for this, I will use Z of T if it is a continuous time random process. But if I do not want to distinguish a continuous time and discrete time complex random processes, I will use the subscript. And for complex valued vector random process, I may use something like this for continuous time vector, a complex vector random process. And for discrete time case, I will use this notation. By the way, I didn't have enough time to put why we consider these complex valued random variables, vectors, processes, and vector valued processes. So I will try to cover this if we go up to this point today. And then also, I will briefly talk about widely linear processing over complex signal. Okay, so this is the page we are going to cover. Z is a complex random vector. What does that mean? Each entry of Z has what? Has real part and the imaginary part. Right? And this can be written as real part vector plus J times the imaginary part vector. Got it? So that's why Z can be written as some X vector plus J Y vector, where X and Y are two real vectors. Especially, we have to know the joint distribution of these two vectors. Otherwise, we do not have a full characterization. Anyway, so complex valued or complex random vector Z of length n consists of two jointly distributed real valued random vectors X and Y of length n each. Got it? So since this is the definition, it is very easy to define the joint density function or density function of the complex random vector by what? By simply using the joint density of the real part vector and the imaginary part vector, okay? If it exists. CDF characteristic function, all can be done in this way. Very simple. Now, given that, we define the expectation or ensemble average of the random vector. First, here goes the mean vector, the same notation as before. And from this definition, we can easily see that the mean vector of a complex valued random vector is simply the mean vector of the real part plus J times the mean vector of the imaginary part. Now, let's consider a correlation matrix. What is a correlation matrix of a real valued random vector? Suppose X is a real valued random vector. Then what is this notation? It's defined as expectation of random vector X times X transpose. So what does this mean? This is a square matrix, and its ijth element or entry is what? Is simply, this is row and this is column. So row, column, expectation of ith random vector times the jth random vector, right? Because you can write it as x1, x2, dot, 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 xn, and this one becomes x1, x2, dot, 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 xn. So ij's entry, you take the i's and you take the j's and multiply, right? You remember that from your high school or not? We learned it when we were high school students, but it seems that our Department of Education dummifies our students, taking out the matrix out of the scope of high school math. That's a stupid decision, I believe. I heard that they are going to put it back because of this, how to say that, popularity of AI and machine learning. And everybody says that linear algebra is the foundation of mathematics for machine learning. So that's good. But anyway, so do you see the difference between the correlation matrix of a real value random vector and a complex value random vector? We use Hermitian transposition. What does that mean? So if we write this, expectation of Z1 up to Z sub n, and here goes Z1 conjugate up to Zn conjugate. So the ijth entry of the correlation matrix is what? Expectation of Z sub I times Z sub j conjugate. Got it? You take the i's component and j's component and multiply. So this is very similar to the sorry, not yet. And this is correlation matrix. And now we can define covariance matrix. The difference is that from Z, we subtract the mean vector, and then, so we center, we perform centering of this random variable so that we have zero mean, and then we take the Hermitian transposition. So covariance matrix is the correlation matrix of Z minus mean of Z. Got it? And this looks very similar to our variance definition, because when n equals 1, this covariance of Z equals just the variance of Z, right? Modulus squared, because we have just the Z and Z conjugate, which is Z modulus squared. Got it? So as you see, the correlation matrix and covariance matrix misses a lot about the second order moments among these complex random variables. So we define complementary correlation matrix and the complementary covariance matrix of the complex random vector Z. It's similar to what we've seen for a complex random variable. Got it? So here we use just transposition. Then all the second order moments of the real part random vector and the imaginary part random vector can be obtained from these two. Got it? Of course, given the mean vector. So you can easily perform the same ideas as something like this. By the way, even some people define circularity of a complex random vector. So here goes some definition I really hate, but they say that Z, a complex random vector, is circular. And what do you guess? Z times e to the j theta has the same has the same distribution. When n equals 1, length equals 1, this definition reduces to the circularity of a complex random variable. However, it seems this multiplying e to the j theta, kind of rotating every component of z using the same angle, seems too restrictive definition. But anyway, some people love this definition. So if these two complex random variables have the same PDF, they say it's circular. I hate that, but anyway. Another one is what here? Propriety. A complex random vector is proper if, what do you guess? The covariance matrix, sorry, the pseudo covariance matrix or the complementary covariance matrix, this one, vanishes. What does that mean? Equals a zero matrix. Then you can easily show what? The real part covariance matrix and the imaginary part covariance matrix are identical. And what? And what do you guess? So let's expand this, okay? Because it's confusing. So you have, let me just we have to subtract, right? Subtract the mean. So we have x minus mu x plus j y minus mu y. So this is the first vector, right? And second one is x minus mu x. And we have transposition. So we have four terms. The first one is what? This times this. An ensemble average. You have covariance matrix of x, right? And then let's consider these two. Then you have negative covariance minus covariance of y, right? And then what? You have this. So j covariance x and y, right? And what about this? J covariance of y and x. So if this vanishes, which means zero matrix, what does that mean? Covariance of x plus, sorry, covariance of x equals covariance matrix of y. And what? Let's take a look at the imaginary part. You have covariance of x comma y plus covariance of y comma x equals zero matrix. What does that mean, by the way? What does this mean? If x and y are of length 1, they are the same, right? Same thing. Times 2 equals 0. What does that mean? That is 0. However, here it does not necessarily mean that each one is 0. Got it? But we can say that two implies what? Two implies covariance of each entry xi, yi. So you take the ith entry. So this is the real part of z sub I. And this is the imaginary part of the z sub I. They are uncorrelated. You can show this. Okay? So you may not immediately understand this, but it's kind of sounds correct because if n equals 1, what does this mean? Uncorrelated. And we've already seen, right? So at each nth position, the real and imaginary parts are uncorrelated. However, this correlation, the covariance matrices are not each 0. Right? What does that mean? Each one looks like this. So diagonal entries are zeros. Right? But off diagonals are not necessarily 0. Anyway, here goes additional one. So we have propriety. And of course, we want to have what? Proper complex Gaussian random vector. And here is the result. Suppose given a complex valued random vector, it's Gaussian. What does that mean? I haven't yet said it's proper. What does that mean? You have a complex Gaussian random vector. The real part and the imaginary part, these two random vectors are jointly Gaussian. That's all. However, if we add propriety, we have something interesting. That is this result. Again, the density function looks very similar to a real valued complex Gaussian random vector. So compare it with a real Gaussian random vector. So let me have strange notation, but yeah. Yeah, something like this. So this is the mean vector of real Gaussian. So when it's real, Gaussian means normal. Okay, so we use n here. By the way, if it is Z is a proper complex Gaussian, we use complex normal. Okay, so probably you've already seen from research papers or other textbooks, Z follows the distribution of complex normal with mean mu sub probably 0 if you want. And covariance CCCZZ if you want, okay? Something like that. And in this case, the real case, what was the joint density function? You had 1 over square root and 2 pi raised to the power of n. Here, n is the length of real random vector, real Gaussian. And here, what did you have? Determinant of Cxx, the covariance matrix of real Gaussian random vector. And you had the exponential. And you had 1/2 times x minus mu x transpose C inverse times x minus mu x. So this was the real case. Now compare it with proper complex case. And you have no square root, right? No 2, but exponent n and determinant of the covariance matrix. You have exponential function. You don't have 1/2, but you have 1. And here you have covariance matrix inverse. And you have a quadratic form after centering your random vector. And if you do not, if you are not sure about your memory, just reduce it, just simplify, as I always emphasize, simplify to what? One-dimensional case. And I emphasize that in one-dimensional case, what did you have for the Gaussian random variable, proper complex Gaussian random variable? So let's put n equals 1. You have a pi. And what is this? This is just sigma squared, right? And then you have, this is 1 over sigma squared. And you have a complex number conjugate and complex number, which is the modulus squared. So everything is consistent, okay? If you are not going to derive, you have to memorize correctly. So this is the what? Special case of this result. Got it? By the way, from this 1 and 2, how can we come up with that one is in our supplementary handout. I really handwritten the derivation, if I remember correctly. Okay, now let's move to complex valued random process. So now you have z subscript t, z of t, if you want. So consider a continuous time complex random process z of t. It has what? Real part random process, and the imaginary part random process. And they are what? Jointly distributed. What does that mean? If you sample at any instance, for example, m instance from x of t, and you sample n instance, so you take n values of y, and you have m plus n length real random vector. And if you know how it is distributed, right? You say they are jointly distributed. So you need that. Given a complex random process, we can define almost the same thing. So we can define nth order CDF, PDF, PMF characteristic function of Z, right? Because it's now, whenever we talk about this, we take a length n complex random vector. And that is equivalent to specifying the joint, these stuffs for the real part and imaginary part. Now, what about stationarity of a complex random process? What was the stationarity of a real random process? We had many levels of stationarity, right? In terms of the first order PDF, we defined what? Stationary to order 1. By using the second order PDFs of a random process, we defined stationarity to order 2. And in that way, we defined stationarity to order n. And eventually, we defined the strict sense stationarity of a real valued random process, right? Since these stationarities based on nth order PDFs or PMF or CDFs are so strong, we defined another one, something loose, somewhat wide sense. What was that? Yeah, wide sense stationarity. And that was defined as what? Constant mean function and time difference only dependent autocorrelation function, right? And then what did we do? We defined joint stationarity of 2 real valued random processes. We defined joint y-sense stationarity of 2 real valued random processes, right? And that may be helpful because here Z has 2 real valued random processes. So first, how do we define stationarity to order 1? The simplest definition is that Z of t, Z of t sub 0 and Z of t sub 0 plus delta for any delta has the same, have the same distribution. That is stationary to order 1. In order for this to be satisfied, what do we need? X of t0, y of t0. A length 2 random vector, and x of t0 plus delta, y of t0 plus delta. These 2 random vectors are what? Have the same distribution, right? And in this way, you can define any stationarity to order n. And what would be the strict sense stationarity of a complex random process? Z of t as an entire random process and Z of t plus delta as an entire random process have the same distribution, right? So delay or selection of your time origin doesn't matter when you talk about distributions. That is the strict sense stationarity. So far, so good. What about this lemma? If Z is stationary, something's wrong. Yeah, this lemma is that complex random process is stationary if and only if these are jointly stationary. Here means strict sense, okay, jointly strict sense. Does it make sense? You can easily show. And another one. So we want to define Y-sense stationarity, and that has a headache because different people define Y-sense stationarity in different ways. And first definition, that is naive, is that expected value of this complex random process is constant for all t. What does that mean? It's a constant function of time t. And that value could be any complex number. And second one is what? They use autocorrelation function defined as Z of T1, Z of T2 conjugate equals there exists some function, though we use the same name R sub ZZ, is dependent only on the time difference for all pair T1 and T2. Some people say this way. And I really hate, but this is so popular definition. If you were the first person who defined the Y-sense stationarity of a complex random process Z, how did you define? Probably you remembered that a complex random process has real and imaginary parts. So probably you remembered joint Y-sense stationarity of two random processes, and you may wanted to use that, right? So probably you would have said that a complex random process is Y-sense stationary if real and imaginary parts are jointly Y-sense stationary. Unfortunately, this definition is not equivalent to that one. There is another one that is the same as what I just told you. There exists a single variable function that is function of time difference. And third one is that you take the complementary autocorrelation function that does not have conjugation. So here, this conjugation disappears in this definition. And there is a single variable function, force of habit, that is also named R tilde sub ZZ, and that is function of time difference. Okay, and you can easily show that this second definition is equivalent to real and imaginary parts are jointly wise and stationary random processes, real random processes. Got it? However, definition 1 is so popular, given that some people, including me, call this as second order stationary. And this is called wise and stationarity. So WSS, SOS, second order station. However, some other people call second order stationarity as totally different definition, so you should be careful, okay? The problem in this real world is that people use different definitions and you know what happens if people use different languages. The Babel Tower in Bible, right? Well, it's very simple to collapse the tower. Let the people have used different language. Anyway, so these definitions are so simple, right? Mean function, autocorrelation function, autocovariance function, complementary or pseudo correlation function, and complementary or pseudo covariance function. Right? And here, as I told you, this is the popular wise and stationarity definition. But I really love this, but this is so popular, right? So I would say these definitions 2 and 3 as second order stationary. And first one as wise and stationary. Got it? Now, before we move to, let's talk about the Gaussian here. Proper complex random process. And by the way, am I ready to talk about that? Just a sec. Yeah. So here goes the definition. A complex random process is proper, or let me write it again. If, again, you use what? The complementary covariance function. If the complementary covariance function defined as expectation of z of t1 minus mu sub z of t1 times z of t2 minus mu sub z of t2, no conjugation equals 0 for all t1 and t2. Okay. So pseudo covariance or complementary covariance vanishes for all pair of t1 and t2. Then a complex random process is proper. Otherwise, it's improper. Now, we want to define a proper complex Gaussian random process. How do we define? How do we define? What is Gaussianity given a random process? But this is complex random process. So actually we are given 2 real random processes. Real and the imaginary parts. Simply, first, Gaussianity means these 2 random processes as real valued random processes are jointly Gaussian. So you take any m samples, any n samples, then your length m plus n vector is real Gaussian. right? That is Gaussianity. What is the propriety? Your complementary covariance function vanishes for all pair T1 and T2. Got it? So first, xt and yt are jointly Gaussian, and 2, proper. And we will see more about this later, okay? Not right now. At this moment, I'm going to introduce you a lot of definitions only, not the consequences yet. Now, we move to a vector valued, we increase the complexity. Higher and higher, okay? So suppose we have a vector valued time function with uncertainty, and each entry is complex valued at each time instant. Got it? So we have z underscore of t. Got it? So you have to understand my notation. The simplest example of a complex vector valued random process is when we have two complex random processes. So this I may be the ith entry, and this j may be the jth entry. Got it? And cross correlation, cross covariance can be simply defined this way using conjugation. Got it? Complementary or pseudo correlation and covariance functions can be defined without conjugation. And in order to know all the second order properties, we need not only the correlation or covariance, but also the complementary correlation or complementary covariance functions. Remember that. And here, two complex processes are jointly wise and stationary. Then what? Cross the each one is what? Each one is wise and stationary. And the cross correlation function is a function of time difference. If they are uncorrelated processes, what does that mean? Cross covariance function vanishes for all pair of T1 and T2. Here, it seems that I'm not consistent in writing down T plus tau part, but anyway, I will correct it. It doesn't matter because anyway, it's 0. Yeah, anyway. So orthogonality in terms of correlation and complementary correlation. Uncorrelatedness in terms of the covariance and complementary covariance. However, some people just do not use complementary correlation and covariance when they define uncorrelatedness and orthogonality. I really hate that. So whenever you see some people talk about joint wise and stationarity, uncorrelatedness, orthogonality of complex random processes, ask him or her, what is your definition? Got it? Because a lot of people use these definitions differently. Okay, anyway, let's see. Here is the mean vector function, right? It's a vector valued function of t. And you have what? Matrix valued function of t and tau. That is the correlation function of vector random process. Covariance function, covariance matrix function if you want. Complementary correlation matrix function. Complementary covariance matrix function. Complementary covariance matrix function. And here you use Hermitian transposition, and here you use just ordinary transposition. Got it? And vector random process is proper or proper complex. What does that mean? This function is a zero matrix for all t and tau. Got it? And we can also add Gaussianity. we can increase the complexity in any way. Got it? So you've seen some definitions. And it seems it's done for my handout, but as I announced in the beginning, we have my handwritten, very old handouts. By the way, you can even watch my lecture, probably much fat. If you go to this site, okay, probably you click that one. Yeah. And go to schedule download. And you have handout 5 and even videos. Okay, is it? Probably these are all not available, but anyway, long ago. Yeah. 10 years ago, something like that. Anyway, let me very quickly cover, because I found that many of you are lack of knowledge on Gaussianity. Okay, so let me be quick. So first, let's review real Gaussian. Okay, so what is characteristic function of a real Gaussian random vector? This is the characteristic function. Okay, see, here you have e to the, and whenever you have e to the, we as an electrical engineer, we remember Fourier transform, e to the j 2 pi ft or j omega t, same, e to the j omega, and here goes the mean vector, and u inner product, this vector valued omega and vector valued mu. Got it? So this becomes a scalar. Now, you remember from signal gen systems, Gaussian function in the frequency domain is also Gaussian function. And this Gaussian function means that e to the negative something squared. And here you have e to the negative something squared. So in the one-dimensional case, you have omega squared, right? So this is the characteristic function. By the way, I may give you, for example, in the midterm exam problem, as given complex, proper complex Gaussian. This just says complex normal, but usually we mean proper complex. Got it? When we use this notation. So Z is a proper complex Gaussian with mean vector mu and covariance matrix C. And what is the characteristic function of Z? And also, what is the characteristic function of Z? And it is highly likely you use real and imaginary part. So second one would be simplify it as simple as possible. And if you want to know the answer to this question, read Populist textbook. Actually, Populist, our main textbook by Populist, has the answer to this question. As some theorem, some people's name is there, Goodman or something. I do not quite remember. Anyway, you've already seen in real Gaussian case, this is the general joint density function when we have invertibility of the covariance matrix. So if the covariance matrix is not invertible, what happens? We need impulse fans. Okay, so let me show you some special impulse fans if I still have it. Yeah, something like that. Okay, we need to rotate, but in the 2-dimension, right? Let's say this is x1 and this is x2. The density function is an impulse fence. It seems that this has finite height, but actually it is not. Okay? So we may have impulse fence if the covariance matrix is not invertible. Especially when we have length 2, we can simplify this formula as you've seen already in your quiz 1, right? We can always rewrite the covariance matrix as the variance of each components and standard deviation of each components and correlation coefficients, and then write it this way. Another one you need to remember is that since the density function is parameterized by mean and variance, right? Your higher order moments are also parameterized by mean and variance. And here goes the very simple one, especially the central moments, right? Due to the symmetry, your odd order central moments are all zeros, including the first order, right? Because if it is 1, your expectation of x minus mu is 0, right? So every odd order central moments are zeros. And even order central moments are what? Only involves sigma. And sometimes you are confused whether you use sigma square here or not, but as I emphasized again and again, remember x may have a unit. So if x is in meters, then the left-hand side is meters to the raised to the power of n. And sigma has the same unit as x. So here you have sigma raised to the power of n, not sigma squared, right? Something like that. And by the way, this is very, very useful. And also in zero mean case, so when mu equals 0, so this is the example, right? If mu is 0, as you already know, this becomes variance, so sigma squared, right? Third order is 0. Fourth order is 1. You have sigma raised to the power of 4, and you have 3, not 2, and 1. In x to the 6th, you have a sigma raised to the power of 6, and every odd numbers less than 6 up to 1. Got it? So this is the way to remember this result. And here, what I want to emphasize is that you may not need remembering this. Anyway, you can Google and find it. But I want you to remember this. The even order moments are very, very simple, so that you can just write the formula down. That is important. Anyway, what else do we have? Oh, here goes the impulse fence, right? And when we say bell curve or bell-shaped curve, it really looks like a bell. However, be careful. It should be quadratic in the exponent. Got it? It does not say that, okay, it looks like a bell. It has e to the negative some square. Otherwise, you'd better not say bell-shaped curve. And here goes the some representative cases of bivariate Gaussian. So here, this is the Pearson correlation coefficient, or simply correlation coefficient. 0 means uncorrelated. And as you see, with respect to the mean, here you may view this as a real part and imaginary part, or you may say that you have two jointly Gaussian real random variables, and this is x1 and x2, something like that. But anyway, rho equals 0 means covariance is 0, uncorrelated. And in a complex Gaussian case, proper if and only if uncorrelated real and imaginary. So you have circular symmetrical joint density. Here you have correlation coefficient negative 0.5 and 0.9. And if the correlation coefficient approaches 1 or negative 1, the density looks more like an impulse fence. So you have a very thin density function here with rho equals 0.9. And for rho equals 0.5, you have not circularly symmetrical density with respect to mean. So you remember these figures. By the way, this is from a very old textbook by Wozencroft and Jacob, and you never heard of these two authors. The book was written in 1960s, I remember. And it was the kind of bestseller in graduate school when my advisor was a student, okay? And when I was a graduate student, I really wanted to find this book. And suddenly, Amazon started the business, and I found it and purchased. So I still have, I have the book. So this is not from some dark past. I myself copied it. By the way, this theorem is very important, and I already mentioned. Suppose X is a Gaussian, real Gaussian random vector, and you have an affine transformation of it, and it's Gaussian. How do you prove? You use the characteristic function of Y, and you combine it with the characteristic function of X, and you can easily show that the characteristic function of Y is e to the j omega times some vector minus 1/2 omega squared times some vector matrix. What does that mean? It's Gaussian. This form means Gaussian. Okay, and also this becomes the mean vector. Naturally, A times mu x plus b is the mean, right? And what is the covariance? You subtract b and subtract the mean of x, and then you have that covariance matrix. Got it? So characteristic function is always very, very useful when you handle Gaussianity. This part I will skip right now because we will be back when we talk about mean square estimation, because this conditional mean and conditional covariance matrix of jointly Gaussian random vectors are very, very important in deriving even Kalman filter. Now, let's focus more on the CDF and PDF of a real Gaussian random variable. First, 1D. What does that mean? You have a real Gaussian random variable. And here, this is called the Q function. And that is what the right tail probability of a standard Gaussian random variable. And from this, any right tail or left, on any CDF or complementary CDF of a Gaussian random variable with arbitrary mean and variance can be derived. How? You normalize. So you plug in the normalized version of something to X. So it's like you have X is Gaussian with mean mu and variance sigma square. And you want to find the probability of right tail. So some alpha. How do you compute X? Because you compute right tail, and you here do what? Alpha minus mu divided by sigma. Done. Okay. So you standardize it. You center it by subtracting the mean, and you scale by divide the quantity by standard deviation. So Q function is very, very useful. Got it? And Q function is appearing again and again in communications. And it also has some relation with so-called error function that is used in other engineering, even in other electrical engineering side. Let's connect the Q function with error function. I had difficulty in understanding what is the connection between these two, but the idea of error function is related to error. But let's just start from this one. Suppose you have e to the negative y square. Then you have some function like this, right? Right? Now, error function is what? Error function is a kind of this area. Okay? So error function evaluated at x is integration of this e to the negative y square integrated within this interval. But when you increase x to infinity, you want it to converge to 1. So you want proper normalization. So here you've done this. Got it? Sorry, 1. Because it integrates from 0. Okay, but actually this is what you have. By the way, you can easily show that this is the coefficient to make this entire integration to converge to 1 in the polar coordinate. You know the trick, right? You've done it when you were a freshman in the college. Anyway, so this is the error function. And by the way, the error function of x, there is so-called associated complementary error function. And that is called error function complement. And that is just simply 1 minus error function. Now, let's relate the Q function and error function. And this is the result. Q function is simply 1/2 error complementary error function of x divided by square root 2. Now, let's see some properties of Q function because it's so important. And whenever I see it, I really smile because when I was taking the college entrance exam, this figure appeared in one of the multiple choice problems. Anyway, so Q function is a monotone decreasing function. And be careful, this is in linear scale. This is in linear scale, okay? Linear and linear. What if you draw log scale? So you take the log of x, you take log of q of x. What happens? By the way, since log cannot have 0, let's consider this area only. So what would be the shape of this apparently convex part, right? See that? If x is positive, this function looks convex, right? And in log, it looks like this. Okay, what does this mean? In log plot, if you watch some straight line, that line follows a power law. What does that mean? It's a polynomial in linear scale. Polynomial relation between y and x in linear scale. So any high order polynomial, still straight line, even though its slope can be different. What does this mean? Q function goes to 0 very, very fast. Got it? Faster than any 1/, polynomial. Got it? So you remember what is the implication of this so-called waterfall curve? We call this as waterfall curve. It seems I'm talking too much. Anyway, it's a graduate course and I can talk a lot. And another interesting thing, as I told you, first, this is definitely decreasing, right? And as you see, in positive part is convex, or convex cup if you want. But there is some strange property of Q function, which I used when I was writing my thesis and the major part of my thesis. That is, just a second, this part I will skip. That is, where it is? Just a second. Where it is? Did I just skip? I don't have enough time, but just a second. There's too much to talk about. Yeah, I cannot find it. But anyway, sometimes you are handling Q of 1/, something, Q of something inverse. And Q function has very interesting property with that too. Okay, so here I just talk about the first order and second order derivative of Q of x, but you may need something like this. And I really used these properties to prove something. And it was quite, my friends in the lab said that, hey, this is a very interesting property, something like that. Anyway, I used that. So I really remember that one. Anyway, what I want to emphasize is that there are a lot you need to know about Gaussian. So let's continue next time. That's all for today.